When a body is cremated, heated to as high as 1800 degrees Fahrenheit, people think it turns to ash. But that is not what really happens. Most of it does not remain in that chamber. So where does it go? Not symbolically, literally. Here is the rule. Not a single atom disappears. This is not comfort, it is conservation. In ordinary chemistry, atoms are rearranged, not destroyed. And in thermodynamics, energy is conserved. Today I will show you, step by step, what that means for your body, for every atom of you, the moment cremation begins. Stay with me, this gets extraordinary. Let us be clear about something from the start. I am not going to talk to you about souls or the afterlife or anything that requires faith. That is not my domain. My domain is physics. And physics has something remarkable to say about this subject. Something that is, to me, far more astonishing than any story we could invent. The bookkeeping rule is simple. In chemistry, atoms are conserved. In thermodynamics, energy is conserved. Mass and energy can trade places in nuclear reactions, yes. But cremation is not nuclear physics. It is chemistry. So when I tell you that cremation transforms your body, but destroys none of your atoms, I mean that literally, physically. Now, to understand where your atoms go, we must first understand what you are, really are, at the level where physics operates. The human body contains on the order of 7 times 10 to the 27th atoms. Let me give you a sense of scale. That is a 7 followed by 27 zeros. We call this number 7 octillion. If you try to count them at the rate of 1 per second, it would take about 200 billion years, far longer than the age of the universe. And those atoms are not a random mixture. Your body follows a precise recipe. Roughly 65% of your mass is oxygen, not the gas you breathe, but oxygen atoms bound into water and into the organic molecules that run every process in your cells. About 18% is carbon, the universal backbone of biological chemistry. Around 10% is hydrogen, present in nearly every molecule your body contains. About 3% is nitrogen, woven into your proteins and into the double helix of your DNA. Calcium makes up roughly 1.5%, almost entirely in your bones and teeth. Phosphorus accounts for about 1%, in your bones and in ATP, the molecule your cells use as energy currency. And then there are trace quantities of sulfur, potassium, sodium, iron, magnesium, chlorine, and a handful of others. That is the inventory. 7 octillion atoms, in those proportions, arranged in a pattern so intricate that it somehow becomes conscious and capable of wondering about itself. I have always found that fact more astonishing than anything else in physics. In a previous episode, we spent time inside the electron cloud. We saw how electrons occupy probability shells around the nucleus, and how the geometry of those shells determines how atoms bond. Keep that picture in mind, because it is precisely those bonds that cremation attacks. A cremation chamber reaches temperatures between about 1400 and 1800 degrees Fahrenheit. That is roughly 760 to 980 degrees Celsius. That range is not arbitrary. It is hot enough to break the molecular bonds holding your body's chemistry together, but it does not come close to the energies required to affect atomic nuclei themselves. We will return to that distinction. It is important. So what happens step by step? The moment heat enters the chamber, the first thing that responds is water, and your body is mostly water. Water is 2 hydrogen atoms joined to 1 oxygen atom. At cremation temperatures, liquid water becomes steam very quickly. Think about what that means. The water in your blood, in your cells, in every tissue, much of it rises as invisible vapor through the exhaust and enters the atmosphere. Those hydrogen and oxygen atoms, which were circulating through your body just hours before, are now water vapor drifting in the air above. Some will condense into clouds. Some will fall as rain on forests and fields. Some will be drawn up through the roots of trees. Some will be breathed in by other living creatures. They do not stop. They simply change address. As the temperature continues to rise, the organic chemistry of your body begins to combust. Your fats, your proteins, your carbohydrates, your DNA, these are built around long chains of carbon atoms, with hydrogen and oxygen and nitrogen attached in precise configurations. When those molecules encounter high heat in the presence of oxygen, they burn. Most of the carbon ends up leaving the chamber as carbon dioxide, CO2, while much of the hydrogen leaves as water vapor. This is where the carbon of your body goes. The carbon that made up the rungs of your DNA ladder, the carbon in the proteins that moved your muscles, the carbon in the fats that cushioned your organs, it disperses into the atmosphere as gas. From there, plants absorb it during photosynthesis and use it to build leaves, bark, roots, seeds. Animals eat those plants. Other animals eat those animals. The carbon cycles. It does not retire. The carbon atoms that were once part of you will be part of countless other living things over time. They do not stop being useful. They simply stop being arranged as you. The nitrogen in your body, concentrated in your proteins and in the nucleotide bases of your DNA, also breaks free into the exhaust. In a hot oxygen-rich flame, nitrogen chemistry can become several small gases. Some nitrogen returns to the air as nitrogen gas, N2, and some forms nitrogen oxides. Either way, your nitrogen leaves. And that is not a dramatic journey for nitrogen. Earth's atmosphere is already mostly nitrogen gas. Your nitrogen simply rejoins that vast reservoir. But eventually, soil bacteria will fix some of it back into compounds that plants can absorb, and from there it will enter the food chain again. The nitrogen that helped encode everything about you may one day be inside someone else's DNA, shaping traits you will never know. Now here is where it becomes interesting. Not everything leaves as gas. Let us do a thought experiment. Imagine you are a calcium atom sitting inside a crystal of bone mineral. You are not bonded into an organic molecule. You are locked into an ionic lattice, a rigid, repeating structure of calcium and phosphate ions. The main mineral in bone is a form of calcium phosphate called hydroxyapatite, and it is extraordinarily stable. To boil pure calcium into vapor would require temperatures well above what a cremation chamber reaches. And in air, calcium prefers to remain in solids like oxides and phosphates. So what happens instead is this. The organic material around the bone burns away. The carbon, the hydrogen, the nitrogen, gone as gases. What remains is the mineral scaffold. The calcium and phosphorus, still locked in their crystalline structure, survive as fragments. These are then mechanically processed into a fine powder. This is what is placed in an urn. Not ash in the way wood becomes ash. Bone mineral, mostly calcium phosphate, with trace amounts of other elements. It often weighs somewhere around 4 to 8 pounds for an average adult. Now pause on that. A person weighing 150 pounds produces only a few pounds of remains. Where did the rest go? Into the air. As water vapor, carbon dioxide, and nitrogen-containing gases, dispersed, invisible, continuing their journeys. The body does not vanish, it redistributes. Modern crematories can filter some particles, but gases like water vapor and carbon dioxide simply pass through. Nature is subtle, but she keeps perfect accounts. So let me make the accounting concrete, without pretending to impossible precision. On the order of 4 times 10 to the 27th of your atoms are hydrogen. Around 2 times 10 to the 27th are oxygen. On the order of 6 times 10 to the 26th are carbon. And roughly 1 times 10 to the 26th are nitrogen. Those atoms leave mostly as water vapor, carbon dioxide, nitrogen gas, and other simple exhaust gases. Meanwhile, your calcium and phosphorus, fewer atoms in number, but heavy and tightly bound, remain behind in the bone mineral. Add it up and the message is the same. In cremation, atoms are rearranged, not erased. Now I want to mention something from my own scientific history that connects directly to what we are discussing. In the early 20th century, not everyone was convinced that atoms were real. Some thought atoms were merely convenient mathematical fictions. In 1905, the same year I published on special relativity, I also published a paper on a phenomenon called Brownian motion. You may have seen it, tiny pollen grains suspended in water, jiggling ceaselessly in random directions under a microscope. I showed mathematically that this jitter is caused by the relentless, invisible bombardment of water molecules colliding with the pollen from all sides. The motion you could see was evidence of the atoms you could not see. Why does this matter here? Because the atoms we are talking about, the ones that leave a cremated body as gas and scatter across the planet, they are not abstract. They are real physical objects, bouncing and drifting and colliding, following the laws of mechanics as faithfully as planets follow the laws of gravity. When your carbon atoms enter the atmosphere as carbon dioxide, they do not hover politely in one place. They are in constant, vigorous, invisible motion. Within days, some will travel hundreds of miles on the wind. Within years, atmospheric mixing can carry them across continents and oceans. I also want to address a question that comes up often in our series on quantum particles. Does any of this disturb the atom itself? Does cremation alter what an atom fundamentally is? The answer is no. Emphatically no. A chemical bond is an arrangement of electrons. Breaking a bond, burning an organic molecule, producing water vapor, producing carbon dioxide, is a rearrangement of electrons. The nuclei of the atoms are untouched. Same number of protons, same number of neutrons, same atomic identity. A carbon atom that combusted in that chamber is, in every measurable way, the same carbon atom it was before. To actually disrupt an atomic nucleus, to change what element an atom is, you would need energies millions of times greater than anything occurring in a cremation chamber. We are talking about the conditions inside stellar cores, or the conditions of a nuclear explosion. The surface of our Sun is about 10,000 degrees Fahrenheit. The reactions in its core involve temperatures of tens of millions of degrees. Cremation reaches about 1,800 degrees Fahrenheit. The nucleus is completely untouched. When I say not one atom is destroyed, I mean it with the full weight of nuclear physics behind the statement. Now I want to offer you an analogy, because a good analogy carries more understanding than a page of equations. Consider a symphony score, hundreds of pages of notation encoding a complex living piece of music. The score is not the paper it is printed on, it is the arrangement of notes on that paper, the pattern. If you burn that score, The paper and ink are transformed. The cellulose becomes carbon dioxide and water. The ink disperses. But the symphony itself, the pattern, is gone. No amount of gathering the atoms back together will reconstruct the arrangement. A human being is like that score. You are not your atoms. You are the arrangement. The specific, extraordinarily improbable configuration of those atoms that gives rise to memory, personality, consciousness, the capacity to laugh and to grieve. That pattern is fragile. It requires continuous maintenance, metabolism, cellular repair, chemical balance. Death is when that maintenance ceases and the pattern begins to unravel. Cremation is simply a rapid way to complete that unraveling. The atoms endure, the pattern does not. This is not a cause for despair. It is a cause for precision, for understanding exactly what is temporary and what is not. Let us also look at this through the lens of the second law of thermodynamics, the law of entropy. A living body is a low entropy system. It is fantastically organized. Trillions of cells, each running countless chemical reactions in coordinated concert, all maintaining the overall pattern that is you. Entropy, disorder, is always trying to increase, and your metabolism constantly fights it back, using energy from food to maintain order. When life ends, that fight stops, and the universe, as it always does, moves toward greater disorder. The highly organized structure of your body breaks down towards simpler, more dispersed states. Carbon dioxide is simpler than a protein. Water vapor is simpler than a cell. Nitrogen gas is simpler than DNA. The second law is satisfied. Cremation is not an affront to the laws of physics. It is a rapid and complete expression of them. And now consider the scale of time involved. The calcium atoms in your bones were not made on Earth. Calcium is forged in the lives and deaths of massive stars, then scattered through space in supernova explosions long before our solar system existed. Those atoms drifted through interstellar space as dust, were swept up into the cloud that collapsed to form our sun and planets, cycled through Earth's oceans and crust for billions of years, passed through countless living organisms across geological time, and eventually, recently in cosmic terms, became part of your skeleton. After cremation, those calcium atoms may sit in an urn, but that is a temporary address. Moisture will slowly dissolve minerals. Wind will carry fine particles. Geological processes will work on the rest over centuries. Those atoms will re-enter soil, be taken up by plant roots, enter the food chain again, and begin yet another chapter of their long journey through living and non-living matter on this planet. They were here long before you. They will be here long after. For a brief interval, they were arranged as you. That interval is what we call a lifetime. Here is something I find quietly remarkable. Because atoms mix so thoroughly through the atmosphere and the water cycle over long times, a statistical argument can be made, and it holds up remarkably well, that it is very likely the air you breathe contains atoms that once passed through the lungs of people who lived centuries ago. Not metaphorically, physically. Those atoms were exhaled. They entered the atmosphere, they mixed, and eventually, over time, some of them found their way into the air in your lungs. And one day, the atoms currently in your body will be inhaled by someone who has no idea. They will be incorporated into a blade of grass, the wood of a tree, or the shell of a small ocean creature. They will fall as rain somewhere far from anywhere you have ever been. You cannot prevent this, and I submit to you that you should not want to. This is the universe working as it was built to work. Conservation is not a cold, indifferent principle. It is a kind of cosmic commitment. Nothing that exists is simply thrown away. Let me come back to where we began. I told you at the start that nothing disappears. And now you understand exactly what that means. The water in your body, into the sky, into the rain, into living things. The carbon, into plants and organisms across the planet, cycling onward. The nitrogen, back into the atmosphere, and then through soil and bacteria into life again. The calcium and phosphorus, temporarily at rest, eventually re-entering the geological and biological cycles of a living planet. 7 octillion atoms, every single one continuing its journey. The pattern, the arrangement that was you, the configuration that could think and feel and ask questions about the universe. That pattern does not continue. Organized complexity disperses. That is the physics. But here is what I want you to take from this. The very fact that the pattern is temporary is what makes it extraordinary. For a brief moment, a blink by cosmic standards, the universe arranged a small portion of itself in such a way that it became aware of its own existence. It could ask questions, it could do physics, it could look at the laws that govern it and feel something like wonder. That is not nothing. That is perhaps one of the most improbable and precious things the universe ever does. In our next episode, we will ask a different question. What happens to your atoms if you are buried rather than cremated? The destination is similar, the atoms continue, but the journey is different, and the chemistry of soil is remarkable. And if you are curious about what happens to atoms in the deepest reaches of space, in stellar nurseries and supernova remnants, that is coming soon as well. If this episode made you look at the world a little differently, or if you found yourself thinking about atoms for the first time in a long time, I would be glad if you subscribed and left a comment below telling me which fact surprised you most. Curiosity, after all, is the beginning of everything.